Okay. So this is building off of the stuff that Kate introduced earlier. So let's just get into it. Maybe. Okay. So this is what we're going to go over here, and some of it's a review and some of it's new, but taking the concept of the perfect pinhole model and the math associated with that, but then looking at how we introduce distortion by introducing a lens to the camera and how we're going to account for that in our math equations and go from the world to undistorted coordinates to then the distorted coordinates because we're working backwards. So this is the review of what Kate told us about with that ideal pinhole camera. So we have the little pinhole opening where the light comes through and projects the image onto the image plane, the image sensor, a focal length different distance from the focal point. And then we're working with the virtual plane so that we can look at the object of interest in right side up. And so this is a camera without a lens, so a perfect pinhole camera concept. And so, yeah, the light rays pass through that onto the image plane. And then, so here are, like Kate told us about, everything can be represented by similar triangles and nice, easy math relating the world 3D object to what we see in our camera image. Okay, so this is still a review of the math that Kate showed us without the pretty colors. But what we're going to focus on in this lecture is how to solve here for the K matrix, our focal length, which again is that distance from the focal point of the camera where the light comes through and our image sensor and or the virtual image plane, so if we want to look right side up. So that focal length, the principal point, which in a perfect world would be exactly in the center of your image, but it's not always. So accounting for maybe that slight shift, center of the image, the principal point. And then if there's any skewness in your pixels, so if you don't have a perfect square pixel, maybe it's kind of a little trapezoid shape, we can account for that in our K matrix too. And so we're solving these parameters here as part of that whole system of equations. And we're also going to do some of the distortion magic down here where we're going from world to undistorted coordinates, but then we need to distort into add our lens and distort into what our camera actually sees. And so the reason we have to add the lens is because if we had a perfect pinhole camera, a teeny tiny hole, the time that you would have to have an exposure to let enough light through to really image the entire scene on that sensor, you'd be there for a long time. And so we have to open that hole up so we can get more light in. But if we have too big of an aperture, too much light in, the light rays are coming from different directions and they aren't able to all be focused on the sensor. So the image would be a little bit blurry. So that's why we add that lens in front of our focal point to direct all the light rays onto our image sensor and get a nice, crisp, clear image. But by adding that glass kind of curved lens, we're bending the rays and we're distorting those light properties. So we don't have perfect similar triangles anymore. So we're gonna, in the real world, we need to add a lens to get that better image. And so we're gonna account for that in our equations. Is this a movie? Okay, maybe not. Here's two examples from some drone imagery. This is a Phantom 2. You can see the distortion in this image, really strong barrel distortion. When you look outside, the horizon should be straight. The image on the right looks to be a lot better, less distortion. But if we take a closer look and draw that straight horizontal line at the horizon, we can still see, there's a little bit of distortion. So just, there's one more. Just for good best practice, we always want to do a lens calibration, and we want to measure for any kind of distortion that there might be, even if you think you have the best camera in the world. So that's what we're going to learn about here. In the distortion, there's two types of distortion. There's radial distortion and tangential distortion. And so the radial distortion is when the light rays bend differently near the edges of the sensor versus the center. And so here is, no distortion, no radial distortion, perfectly square pixels. Over here is an example of what we call pincushion distortion. So it has a negative radial distortion. And so the image magnification increases with distance from the optical axis. So increases on the edges. An example of that is like a telephoto lens. And then on the other end of it would be positive radial distortion or like barrel distortion, kind of like what you see in the GoPro where the image magnification decreases from the optical axis. So something with a really wide field of view. And then, so that's the radial distortion. And then the other component is the tangential. And so examples here on the right are when the lens here and the image plane aren't perfectly parallel. And so that's going to change the way that the light comes through as well. And so that is referred to as tangential distortion. And we can measure both of those with our calibration procedures. So now we got to go back to the math a little bit. And we use what's called the Brown distortion model, no relation that I know of, but automatically makes me, I guess, an expert on it. And so we use the Brown distortion model to compute to account for the distortion in the image. And so first we take our pixel coordinates and put those into normalized image coordinates. So our image has, a U number and V number of pixels. And so for each pixel, we can create a normalized image coordinate by translating based on the principal point, the center of the image, and dividing by the focal length in pixels. And as you can see here, the focal length can be different in the X and Y direction. So that's also something that we're measuring and accounting for. And so by doing that, we have now normalized image coordinates. Here's another, oops. And with the normalized image coordinates, then we can compute a radius. And so that's translating the pixels into this radius in normalized image coordinates. And we can do this for the distorted pixel coordinates and the undistorted pixel coordinates. So now we have just represented here as one value. And then we can put these use these to compute our distorted points. So this top equation is the full equation here that accounts for radial distortion and tangential distortion, and where dx is represented down here. Here are R squared, or our degrees are those normalized pixel coordinates in radius, and these colored variables here are actual radial and tangential distortion coefficients. And these are what we're solving for by doing our lens calibration. And we can get these, we use the Caltech Toolbox that we're going to do practicum next. And so we solve for these distortion coefficients to plug them into these equations to go from our undistorted pixels to our distorted pixels. And as noted here, the Caltech Toolbox will spit out these coefficients, but they're not necessarily in order of 1, 2, 3, 4, 5. So the first two and the fifth one are radial coefficients, and the third and fourth are tangential. But this is all documented here in the codes and the practicums, so we'll be able to keep track of that. And so just all the steps in one slide, a summary. We want to, like Kate told us, we're going from world to undistorted to distorted. So here we're computing our undistorted pixels in normalized image coordinates by accounting for the principal point and the focal length. Then we're converting that to a radius and solving with our already solved distortion coefficients. We can go from our undistorted coordinates to distorted, and then we can then solve for our U and V pixel coordinates in distorted by just going from the normalized image coordinates back to the regular real image coordinates. And so this is an example here where this would be our undistorted point, but because of the distortion, it's here on our image pixel. So these are the steps that will go from undistorted to distorted. I think that's it.
I have a question.
Yep.
Sorry, it's been bugging me kind of all morning. What causes there to be different focal lengths for the X and Y direction? Do you have any idea?
It would be because since we're not in a perfect world and perfectly, would it be more because of the tangential or radial? Like, so because we're not maybe parallel our sensor and our lens. Yeah, so if you draw the line from a U and a V, it's going to be slightly different distance, yeah.
And there are some reasons why manufacturers design them with different focal lengths. So this just allows for.
Pro tip.
Okay. This we'll see, I think, when we look as we continue through the practicums and the codes, but the A_format intrinsics takes, I believe it takes the Caltech Toolbox results that we're going to do in a second and puts it into this intrinsics variable that the rest of the quantitative coastal imaging toolbox uses. And so the intrinsics variable has all these components. And so we have our principal point, our focal length in X and Y, and then our radial and tangential distortion coefficients. But this function should take Caltech and put it into this variable, right? Yeah.
So that, we'll go into that function, but basically you can either do it from another program, Metashape, you could use the MATLAB calibrator, and then you can just enter it manually too. We use the Caltech one mostly just because it's free and you don't need a MATLAB toolbox. But you know, there are options where you could just enter it manually as well.
Yeah, and so if you do it manually or a different method, then you just need to make sure that intrinsics 1 through 11 are these actual variables. And yeah, this slide goes into, if you are familiar with other types of software for doing calibrations or structure for motion, Brittany has actually come up with a nice table of how to relate the different results into a similar variables that we put into this intrinsics variable. And so the point being that however you do the calibration, you want to make sure, and we'll go into this in the practicum too, that when you're taking your calibration images, you want your camera set up to how it's going to be when you deploy it as much as possible. And so if you're going to be recording videos, you want to do your calibration in video mode. If you're doing still frames, you want to be in still frame mode when you capture your calibration images, and you want to make sure all pixels in the frame are utilized.
You want to try to, when you're holding up your target, don't just take a picture of, just keep taking a picture of the thing in the middle of the target. You want to try to get the target up in the corner of the picture, the other corner.
Yeah, and we're going to definitely show examples of that. Okay.
I think also, sorry, that was just, you're using structure for calibration from structure for motion, particularly on the coast. Like if you're flying and you just have water on one side of your image, it's not going to do a good job of calibrating the water side of your image. That's, I think, what that was.
And then in the quantitative coastal imaging toolbox, there are these functions that can go from to distort your images, so undistorted to distorted, or the other way around, distorted to undistorted. And in the distortion case, the flag again that if you're going from undistorted to distorted and a feature is outside of your distorted image, it will flag that and doesn't try to wrap around or have missing pieces. So those functions are available. And this is just taking it to the next step. Once we have our distorted image, how we just will, and we'll go through this in a future lesson about rectifying images. So again, we're doing XYZ to undistorted, accounting for the distortion by then creating our distorted coordinates, and then you can interpolate the RGB values to those new distorted coordinates. So we'll have more examples of that as we go through the day.
It's quicker to take a few points and make them distorted rather than to take the whole image and undistort it, if that makes sense. Because like you have thousands of pixels in your image versus 100 points that you're trying to calculate. So it's just easier to go that way.
All right. So in summary, I feel like I'm just repeating the same things, but it's good. We're learning how to solve our intrinsics and then also doing the distortion magic to go from undistorted to distorted. And so the take home points are you always should be calibrating your camera. That's necessary to go from the world and back and forth between distorted and undistorted. And we're going to be showing an example of how to use a calibration toolbox that helps us solve for the K matrix and also our radial and tangential distortion coefficient. All right, Brittany just left and now I need to learn how to run my live script. So on the USB should be Is this a USB? All right, well, we'll start with this practicum and maybe show you back. So on the USB somewhere is a live script. I think that it might be lens calibration demo. Is there a folder that says that? Well, how do I run my live script? But I guess I'll do this. I'll do these slides for you. There we go. Okay. I'll show some slides before we start punching buttons. But we'll go through. So yeah, here we are. We're going to take calibration images so that we can go between distorted and undistorted. The Caltech Calibration Toolbox, this link is probably wrong because they've actually, I think, published the code, but it should be on the USB drive, or if you downloaded it before we came, it's essentially Capital Toolbox Calib, I think. But yeah, here's the steps we're going to go through if we were going to do lens calibration collect before we deploy a camera. So we've said this before, but we're going to keep saying it, that when you take your calibration images, you want the camera to be in the mode is ideal as to how you're going to deploy as possible. And so if you're going to take video, do your calibration images and video still or still. And you want, essentially, we're trying to take the whole image sensor and get the calibration pattern covering the whole field of view. And so you want to be, you want your target to be on all sides, on all corners, because whatever you're looking at in the world, you want all of that to be, every edge and part of the image to be accounted for. And so there's a couple different ways you can take your calibration images. You can put it on you can put the calibration pattern on a surface and keep it still and move the camera, or you can hold the camera still and move the pattern. So that's the two examples here. And you can use any kind of pattern you want, but you want the squares to be of a known size, of equal size, because by taking all these pictures, we're solving and telling it that this is the size of those squares. And if it's not that size in these corners or at this place, it's because of distortion. And so this is a pattern, I guess, that Army Corps uses. This is huge. We print a little pattern out and put it on a little clipboard. It's up to you, and it's up to the environment you're in. This calibration was done in the lab. This calibration was done on site. So we went on top of our building. We focused our camera. We got it all set up how we want the field of view to be. And then we did the calibration on the top of the roof. And so what these two examples are showing is, again, you're covering the whole, you want the whole image to be accounted for and have examples of this calibration pattern. So you might want to get, the the pattern taking up the whole image, but then you want to move forward and backward from your camera. You want to tilt have different angles of the calibration, so that we can, again, account for distortion in all parts of the image sensor. And so I think this shows a good example of what a series of calibration images should look like. Close, far, hold it into each corner. It's much easier to do with two people. Rotate it in and out at the edges and spreading it throughout the image. And you'll see the number of images. You can collect as many as you want. About 20 is a good amount, and you'll see soon why you don't want to do like 2,000, because there's a manual step involved. But you just want enough to make sure you're covering the full area and different angles, different distances from your camera. And so I'll go through these steps quick because we'll do the live demo, but we're going to run the calibration, the Caltech Calibration Toolbox, which the main function is called calib_GUI. We'll load our images, enter our image names. Yeah, we'll go through all these steps. Extract the grid corners. Yeah, let's just get into it. Oh, this is a step 2. Why are there? We want to measure all 5 distortion coefficients, 3 radial and 2 tangential, and that is not the default of the Caltech Calibration Toolbox. And so in the live demo code, this is included, but if you're doing it separately at a later time, you want to manually set this variable s_dist, estimate distortion, to all 5 to be 1. And so that tells it to compute all 3 radial and all 2 tangential coefficients. And so this is an example of the Caltech output. Once you go through all the steps and hit calibrate, it tells us here our focal length, X and Y, our principal point, U and V, X and Y, skewness. I think this is set to 0. I think we typically assume skewness of 0 on a decent camera. And then here's our distortion coefficients, KC, and you'll see it 1, 2, 3, 4, 5, where 1, 2, and 5 are the radial, and 3 and 4 are the tangential. That's what we were showing in that slide before. But this is where the codes, Brittany's code, will take these and all this information and put it into that intrinsic variable that we need to continue with the processing. And then the last number here is pixel error. And so that's in pixels, the error associated with the distortion. So you want to get a good enough calibration to try to get this less than 1. If you can get to 0.1, that's even better. But you want to, this is measuring the pixel error due to distortion, and you want to have that be as small as possible. Right? Yeah. Okay. We're going to go through all this. Let's just do it. So in MATLAB, if you have this in practicum_lens calib, there should be this live script here, lens calib_demo live script. So that
Live scripts introduced. Okay, that
it might be a problem.
for super old MATLAB, that may be an issue.
Okay.
Right.
Yeah, that's fine. So I'm just going to run it through section by section. So I'm doing run in advanced, and now it's taking me essentially to line 1 of the code. And so first thing we're going to do is set up our paths, tell it where our calibration images are, and also make sure that the toolbox is on our path. So if you start from practicum lens calib